So I've been working on and I've been spending time understanding how you optimize concurrent data structures, or basically writing performant concurrent data structures. And one of the things that usually comes up when we talk about concurrent data structures is how do you optimize cache? That means data that's resident in your cache. So before we get into what is, what's in your cache, etc., let's understand what the cache is. So quick check. I'll just sort of flip to my screen. Can you guys? All of you can see my iPad, right? Oh yeah, you're seeing a black screen. So yeah, that's the iPad. So you can see this. I'm presuming you can see that I'm able to draw stuff. Yes, I just want to confirm because this is I'm just testing this out. Can you see me drawing? Quick confirmation. Okay, cool. All right, so I'll quickly talk about this. So what is the cache? If you actually think about it, you have your computer's memory architecture, which is something like this. You have your core, which is, I'm just going to draw this. This is your CPU core. And then you have your main memory, which is, it's always usually going to be bigger. You will have something that is, I'll just call this main memory. Okay, so with your main memory and your CPU core, you generally, when you want to access some portion of your memory, some part of your memory, your basically your CPU is going to put in a request, and that's going to go over the memory bus, which is straw memory bus, and then you're going to have you're going to be accessing data, which is, these things can be instructions. Let me just pull this down. These things can be instructions, or they can be, or data. Actually, let me just do this. Or data, right? So that's how you've got your CPU core and you've got your main memory. You want to access information. Basically, let's assume that you are, what do you say? You're executing your, you're basically executing your application. Okay. Then you've got instructions and you've got data. The CPU has to reach out to your main memory where these instructions are present, fetch them, execute them, and then whatever is the result of that computation is something that you see. But actually, this is not the way modern computers work, because I'll sort of, I'll just sort of move this out. This is not exactly how modern computers work. There's one more, you can call it intermediary in between, and that intermediary is what we call the cache. So this is the cache. Now, the cache is nothing but it's another type of memory. It's another type of memory, except it's extremely, compared to main memory, it's orders of magnitude faster. So when I say orders of magnitude faster, think about this cache. The CPU actually talks to the cache, and the cache is connected to the main memory. These caches are of different types. You can have something called L1, L2, and L3. L1, L2, and L3, right? So if you actually have these three different types of caches, L1, just to give you a heads, like sort of an idea, L1 and L2, these things take about 1 nanosecond in terms of, basically accessing these caches. This one probably takes about 10 nanoseconds. And the memory, the main memory, this can go all the way up to 100 nanoseconds. So you see there's between your data that's resident in your L1, L2 cache, and data that's resident in your main memory, there's a 100x, difference. And that's why we sort of use caches. It's um, people usually talk about a very simple example. They say, let's say you were asked to get a book, or you were asked to get some material from the library. If you went to the library every single time and got a single chapter, that's obviously going to take a lot of time. Let's say you borrowed the book, brought the book back, and whenever somebody asked you, can I ref this particular chapter, and then you immediately say that, yeah, here's the chapter. So a cache is effectively a temporary storage that's available to you. Its purpose is to provide this, high performance capability that you need when you're talking about any kind of computation, right? Make sense? So I'll just take a pause. Does this make sense? We'll get to the other parts, but yeah, makes sense, right? Yeah, cool. Okay, so what we need to be aware of is this particular thing called the cache. So in our case, when we keep thinking about this cache, I was wondering, when you have a scenario, when you have, let's say, you have a certain, sorry, let me just delete this. Let's say you have some location in memory. You've got a oh, sorry, I need a bigger thing. Just a minute. Okay, so you probably need a bigger, you have some location in memory, and then you have, let's just assume that these are all threads. There's a thread 1, there's a thread 2, then there's a thread 3. All right, all of these are threads. They all want access to this particular location. Some of them are reading and some of them are writing, right? Now in that case, particularly you have let's assume you have something like a queue, a really big queue, where you have a big queue and you have multiple threads that are accessing different parts of your queue or something like that, and there are other threads that are attempting to write to it as well. When this is going on, the question is always going to be, okay, if this is going on, first of all, obviously, how do I synchronize? That means when somebody's writing, nobody should be reading, all of that. So assume that all of that is sorted. There's another bigger problem over here. Once you have the synchronization part taken care of, then you always come to this part of, okay, is my code actually written in the most performant way? That means, am I able to access different parts of this particular queue, fast enough, right? That's another scenario, and that's sort of what I'm looking at. We're not going to be touching that because that's probably going to be a much longer discussion. But effectively, this is what I wanted to sort of cover for you in terms of the L1, L2 cache. And I also wanted to sort of let me pull this down, and I say, the other thing that I also want to say is, let me just remove this, and let me sort of draw this. There's one thing that I wanted to also talk about, which is the hierarchy of caches. In caches itself, you have many different kinds of caches. As I said, L1, L2, L3. So, sorry. You will have something like this, which is, let's just assume that this is your L1 cache. Then you will have your, actually let's take a different color. you will have your L2 cache, and then you'll have your let's take the white one. Then you will have your L3 cache, and then you sort of have your memory, whatever your main memory. You have your main memory. Okay, this is main memory. So one key thing that you guys can keep in mind is, as you go, as you sort of go up in this particular hierarchy, you will see that your bandwidth is increasing. That means you would be able to basically do a higher performance. As I said, if you have 1 nanosecond speeds to access this L1 cache, that means you'll be able to move data in faster and data out faster. So bandwidth increases over there. But as you move down, the size of your caches increase and the latency. That means I already said, depending on where you are, your caches actually affect how fast you are. So over here, the size also increases. So for example, you'll only have something like 64 kilobytes of your L1 cache, and then maybe 256 at your L2 or something like that. L3 will have MBs of cache, maybe 4 or 5 or 6 MB. So next time you're actually buying a computer, you may want to look at the processor, and you may actually want to check how many cache, how much in your cache hierarchy, in the processor's cache hierarchy information, which one has how much, because that does affect performance, right? Make sense? Yeah. So that's another thing that I wanted to cover. So far, does that make sense? Quick confirmation, anybody? Any questions on that part? Okay. All right. So now let me actually move over to the implementation specific part. So far we've talked about this particular piece wherein we were talking about the cache as from a hardware perspective. We were looking at the hierarchy of the cache, and we're also looking at the properties of different caches, etc. Now that you have that understanding, let's actually look at a real example. In front of me, you can see my screen. You can see the VS Code instance, right? I just want to confirm because I had to redo the entire. Okay, yeah. So I basically have a simple crate. If you look at the cargo.toml file, there's not much going on over here. It's just a demo thing that we're going to be doing. I added some benchmarking stuff. You can just ignore that for now. That's not important. I was just doing some other kind of tests. But anyway, I went and I was trying to figure out how can I explain this better with some code. And I think I came up with this particular idea where you could probably use a loop to sort of demonstrate the idea of a cache. Okay, so when we talk about caches, I've actually put together two functions over here. One computes the sum. Both of them actually compute the same, they give you the same answer. And I'll show you that they actually give you the same answer. They do the same thing, but one is faster than the other. And depending on how much data I have to sort of run through to perform my summation or my addition, it'll take that amount of time. So if you think about it, let me actually sort of walk you through this code. First, what do I do over here? I'm just going to put some comments. I just create, create a vector. And then here I'm basically, populating the vector. So what do I mean by populating the vector? I basically iterate over each element of the vector. It's initialized to 0 in the beginning. And then for each element, I'm just sort of, putting a value in there, 0, 1, 2, 3, etc. So at the end of it, this particular vector, which is about, I think it's about 16 million elements. It's going to have 16 million elements in it. Then I create my sum variable, and I loop through it twice. I'm looping through it. There's two loops. There's one outer loop and there's one inner loop. And then all I'm doing is about 4,000 times I'm looping, and every time I loop through, I'm going to pick one index and I'm going to sort of add it. Make sense? You don't have to do this if you actually need to do a summation. You can just do a direct summation, but I'm doing it this way. Either way, if you just do a direct summation, you'll get the same answer, or if you do it this way, you get the same answer. Now, what I'm trying to say is this one is actually taking the help of the cache to perform better versus this one. When I say uncached, it does not mean that, none of this is actually going to be available in the cache. That's not the case. I just named it that way. But just know that it's not the fact that there's none of this vector's data is in the cache. It is, but it's not very efficient, or rather it's not very performant. It's not the best way to write it. That's what I'm trying to say. So before we go forward, can anybody tell me what's the difference between the two? Both the implementations sort of look the same, right? It's a very subtle difference, but I'll show you, it does affect performance quite a bit. Anybody? Nope. Okay. In the interest of time, I'll just sort of quickly get this with. So if you see this particular loop, the order of this expression, or rather the way this expression is written, is different versus this. All right. It's just a very subtle difference. Instead of an x plus 4,000 times y, I do for the second one, I'm actually doing an x times 4,000 plus y. Okay, and then I've also got a bunch of tests where I'm timing my executions. Basically, I run both executions and I then measure how much time has elapsed. And consistently, you will see that there's some difference. So let me get that test run, those tests running. All right, so you see that, right? I hope you can see this. Is it visible? Is the terminal visible? Okay. So is the terminal visible? Can you see my terminal? I guess you should be able to see it because I am sharing my screen. Okay. I think you can see it. So if you see this, the cached version of it actually only takes about 300 milliseconds. And if I basically execute the same kind of computation, I'm taking a little more longer. Now, this is not exactly twice as slow. This is maybe 50% slower, right? Now, 50% slower for the exact same computation just because I moved, the order in which I'm actually performing my computation has changed. This is what I'd call an optimization problem. Basically, we need to leverage the cache better. To to drive this point home better, let's actually increase the value. Let's say I look at 40,000 elements. Okay. So let's just look at that, and I look at even more, an even bigger queue. This is going to really, tax even though I have a pretty fast CPU, it's going to really tax my computer. But before I do that, okay, after I do that, I'll probably run this. I'm just going to run the sum just so that, you guys see it, and just so that you know that the actual result is going to be the same in both cases. But when I do run this, I've just increased it from 4,000 to 40,000. Okay. Now if you see, actually, wait. now if you obviously, because you're now talking about some 16 billion elements or something like that, it's going to take a little bit of time right now. But I want you to see the difference between this one, which is the one that's better, that's where the caching is happening well, versus the one that is probably not making use of the cache as good as the first one. Let's look at both of them. All right. Firstly, you see the answer. The answer is some massive number. We don't care, but that's there. It takes about 34 seconds. Now, what's the second one? I could probably go do a couple of things and come back. Okay, so that's going to take a little while. But this should give you an idea that, yes, you have to, whenever you think about writing production code, and you're thinking about performance being an absolute, as a very important thing for you, you have to sort of look at your cache and how well is your code actually doing with cache. And this is not something that the compiler is going to do for you. You need to figure this out. That's what I wanted to also talk about. We're so used to dealing with the compiler with Rust because, mostly memory safety and stuff. But this stuff, you, the programmer, or you, the developer, needs to know, how do I build, how do I better optimize my code so that I can squeeze out every drop of performance, right? So that's the quick thing that I wanted to cover about cache locality. Now, the other thing that I want to say is this is basically, this is what we call spatial locality. That means we're talking about memory and the space. We're not talking about another aspect, which is also relevant. It's called temporal locality. Okay. So one of the things that I didn't mention is, actually let this thing complete, but while that thing completes, let me see if I can sort of pull up my iPad over here and show you another example. Okay, so let me go back here. Maybe optimizations need to be disabled. Optimizations need to be. Yeah, I think my voice dropped a bit. That's probably because we're running this. We're doing this really large calculation. That's probably the case. But yeah, I think you should now be able to see it. Can you see it now? The difference is this takes 34 seconds, but this takes 153 seconds. That's almost 5 times. Yep, 5 times. That's a 5x difference when we talk about whenever you're not making the best use of your cache. You can actually, sort of optimize this much better as well. Maybe I can sort of show you that. But before I do that, I wanted to talk about this thing called this, whenever you read up on caches, you'll also read up things like temporal locality and spatial locality. Temporal locality is timing, spatial locality is space. So let me quickly pull this up. Can you see my, sorry, I don't think you were able to see the terminal. Can you see the terminal now? Yeah, so I think I don't think you guys were able to see the terminal, but here's what's happening. This is 153 seconds versus this is 34 seconds. Right? So that's about 5x of a difference. And that's why you really need to know how to sort of optimize for the cache, for your cache. That means to get your data in and out of the cache as much as possible to improve performance in any case that you can. This is not the case everywhere, but whenever you're writing performant concurrent data structures, this is very useful. Maybe at a later point, we'll get into the actual thing that I've been looking at, but at a later point. All right, does this make sense? Okay, so Before we go, the last point that I wanted to cover was this spatial and temporal locality. So basically what the cache looks like is the cache, whenever you look at the cache, it's going to be something like this. I said L1 caches have like 64 bytes actually. So there'll be a cache line that's about 64 bytes, which means that's it. You only store like 64 bytes and that's your cache. And you can have multiple cache lines like this. Okay? You'll have multiple cache lines like this, and each cache line is usually 64 bytes. This is not set in stone. This is very, very processor dependent. Okay? This is very, very processor dependent. Make sense? Sorry, let me go back here. Yeah, so I think I really need to figure out a way to easily switch between these two screens. Otherwise, it's not working so well. So yeah, this particular thing that you see, this is what you call, this is the cache. This is the cache, and in the cache, you can have, you'll have like multiple cache lines. Assume that each cache line is about 64 bytes. And what you're trying to do is, what generally happens is, what happens in a modern processor is, in your main memory, let's say you've got, you are accessing maybe 4 bytes, right? Let's assume that you are accessing 4 bytes in your main memory, somewhere over here. Okay, somewhere over here. Let me actually sort of draw this better. So in your main memory, you are trying to access this particular portion. Okay, I hope you guys can see this, right? You're trying to access that particular portion. What really happens is, whenever you're trying to access that location, the entire 64 bytes that is probably aligned, etc., that's a different story. But around this area, about 64 bytes are directly pulled into the cache line. The reason for that is because, that the likelihood that you will be accessing elements within that range, because whenever you're accessing something close to another thing, so whenever you access something, it's very likely that you're also going to be accessing the next thing that's closest to it. That's why it's called spatial locality. Okay, depending on where, depending on how close to the intended access you are, you may get pulled into the cache line. Okay, that's why what happens in the previous example is, we are pulling in more data into the cache line for each loop that we're going through. We're pulling in, more of the data that we need, and we're using it while it's in the cache. In the second example, in the second verse, we are not making use of that contiguous nature of things. So if your data is laid out contiguously in memory, then it's highly likely that whenever you access an element in that contiguous array, let's say, that information will get pulled into the cache. So this will get pulled into the cache if you're accessing any element in that contiguous memory. That is what we call spatial locality. Okay, that's the likelihood of, because it's based on that likelihood principle. How likely, it's more likely that you will probably access the next element in this array, because you're probably going through a loop. So let me just pull that into the cache line. And when it's in the cache, whenever I'm asking for the next element, it's already in the cache, so I can easily access the next element. But in the second example where I was trying to show you, you're not making good use of the cache, we are, because of the order in which I'm doing the addition and the multiplication, we are probably not pulling in the relevant elements into the cache, and we are always having to reach out to main memory. That is why you have that discrepancy in the amount of time it takes to compute that. Right? Does this make sense? Right now I'm on the iPad. Can you see the iPad? Can you see this one? I think you can. Okay. All right. So, any questions so far? Right. So this is what we call spatial locality, and then temporal locality is another element. I don't want to get into that. The reason I don't want to is because I don't have an example for you right now. But temporal locality is very simple. Now you know that elements that are closer to the actual one that you're accessing get pulled into the cache. Also, think about timing. Let's say you're doing an operation, and then you know that the subsequent operations are also pretty much the same. So you might want to have them ready. They may not be located closely in memory, etc. But basis timing, that if this operation is happening, maybe you'll definitely do the next step is probably going to be this operation. So you probably want that, that sort of a strategy as well when you're trying to improve performance. But that's for another day. We'll talk about that. So two kinds of cache locality problems that can be solved are two kinds of cache locality that we can be dealing with is spatial locality and temporal locality. Right? Any questions on this? I hope this is, with this example, it's making a lot more sense, right? Just the order, that's all I did. I changed this to this. One took 34 seconds, the other one took 153 seconds, as you can see here, right? Okay, so before we wrap up, any questions? Okay, no questions? Okay, so questions going once. Please share the code. Yeah, I'll upload that. I'll put that in GitHub right away after this stream. Anything else? Yeah, there's not much in this stream. It's just, something that I was working on. I'm like, okay, yeah, this may be cool to sort of show you. Like, I was thinking about how do you showcase something like this with an example. It's not very straightforward. You really have to, because modern computers have a way of, caching a lot of stuff. I was trying to figure out how to do this, and loops are the best way. Random access within a loop usually helps. Right? Okay. So going once, any other questions? Twice and thrice. That's it, I guess. Since there are no other questions, great. Thank you for joining. I will see you again in another stream. Right? Thank you.